So good morning all of you. Today I welcome you all to this course of electromagnetic field theory. The course code is PHM 704. So as you have in your other courses, this course also has got 5 units, and we will try to finish these 5 units in about 50 lectures. So just to give you an introduction why this course we need to study at all. So we all know there is a force called gravitational force. A well-known force dominating the Newtonian mechanics, and we know that this force decreases as 1 by r square, and the force between two bodies is proportional to the masses of product of masses of two bodies. So if I have two bodies, say m1 and m2, and if the distance between them is r, then this force F is equal to some constant m1 m2 by r square. This is the gravitational force. There is yet another force. This gravitational force acts on bodies, on a macroscopic bodies on macroscopic scale. There is yet another force which is billion times larger than this gravitational force, and there are now two mass entities. So this force is called as electrical force. So electric force is billion times larger than gravitational force. And unlike gravitational force, we had only one kind of mass entity, but in electric forces we have generally two types of mass: positive and negative. And these are the force which hold the matter together, and these are the force between electrons and electrons, these are the force between electrons and protons, and these are the forces between protons and protons. So these two types of masses are basically positive charge and negative charge, and we all have studied that these forces are governed by Coulomb's law. So in Coulomb's law, we say that F, the electrical force F, is proportional to the product of the charges and is inversely proportional to the square of the distance between the two charges. But this force, unlike gravitational force, is enormously large. So now the question is, I have an atom, and the core of the atom has got positively charged nucleus. So now the question is, these electrical forces are manifesting inside an atom. These forces are dominantly balancing the matter. But the question is, if I have group of positive charges, if I have bunch of positive charges, then these charges will repel each other. They will repel each other. And these charges will fly apart. On the other hand, if I have negative charges, bunch of negative charges, then these charges will also fly apart. They will repel each other. with enormous force. But if I take an atom, it has got a heavy positively charged nucleus with large number of protons sitting inside, and also I have electrons orbiting around the nucleus. Now question is, if large number of similar kind of charges are sitting inside this nucleus, why don't they fly apart? Why doesn't this nucleus break? So the question is, inside the nucleus, apart from electrical forces, there is one more force called nuclear force. So this nuclear force, so inside the nucleus is the nuclear force, and these nuclear forces are short range forces. But they are short range forces. So it means I can say if I have a proton and proton, so it will act only between these two protons. They are short range forces, whereas electrical forces are long range forces. They are long range forces. Okay. So here we are doing the comparison between electrical and nuclear forces. So I would like to tell you that gravitational forces are even longer in range than electrical forces, because we experience gravitational force between two heavenly bodies like the sun and the earth. All the heavenly bodies are positioned in predefined trajectories because of these gravitational forces. So these gravitational forces are extremely long range. But if we compare nuclear forces and electrical forces, nuclear forces are shorter in range than the electrical forces. So there is this strong nuclear force which is much stronger than the electrical force that keeps these protons together, that holds the nucleus together. So but these electrical forces are long range, so they sort of act on the entire nucleus, but because their magnitude is much smaller than the nuclear force, so the nucleus generally it doesn't break apart. Now another question is, so we could explain why nucleus is together, it doesn't break apart, but there are electrons in the nearby orbits. I have electrons which are orbiting in some trajectories. Why these electrons do not fly apart? Why doesn't the matter explode? Why all these electrons are orbiting without any problem in some trajectories? So the answer is, if I have to confine an electron in a space, I need to give a large amount of momentum. I need to give large amount of momentum and to confine it in a specific space. So that is the reason that these electrons are in a specific space with some fixed angular momentum, and they are able to orbit around the nucleus without flying apart. But still, this explanation is not adequate. Until now, there is not a satisfactory explanation for why the electrons do not fly apart. This is one intuitive explanation that why electrons are together and matter doesn't explode. Now let us take an example. Is it always true? Let us take an example of uranium. So it is a well-known member of the periodic table. So uranium has got a big nucleus. It has got around 72 protons in the nucleus. So I have uranium, it has got 72 protons. Okay. So because these nuclear forces are short range forces and this nucleus is quite big, so what happens? The moment you lightly tap, so these nuclear forces will decay very fast. Inside, this is uranium nucleus. Okay. This is uranium nucleus. So now these nuclear forces will decay very fast. So if you give a small perturbation from outside, this uranium nucleus breaks into two parts. into two positively charged nucleus. An enormous amount of energy is released, and we call this as an atom bomb. So actually it is not the nuclear energy that is released when a uranium atom breaks, it is the electrical energy. It is the electrical energy that is released, because these nuclear short range nuclear forces, they decay very fast, and it is the electrical repulsive force between the 72 protons which breaks the uranium nucleus into two parts. An enormous amount of energy is released because of the electrical repulsion. So if nucleus are quite big, then they are generally unstable. So this is a famous the famous radioactive compound. So now this was just to give you an idea how these electrical, nuclear and gravitational forces differ in nature. Now we move on to how these electrical forces are produced. How these electrical forces are produced? For producing electrical force, we need a charge. We need a charge. When this charge, this is a plus Q charge, I assume, when this charge is stationary, this behaves differently, but when it is accelerated, say with some acceleration A, then it behaves differently. And an accelerated charge gives rise to electromagnetic fields. Accelerated charge gives rise to electromagnetic field. We know the famous law of Faraday. It says a changing electrical field. A changing electric field can induce a changing magnetic field. A changing electric field can induce a changing magnetic field. Perhaps Faraday's law is the most important discovery in the history of physics. Perhaps Faraday's law is the most important discovery in the history of physics, and this Faraday law gave rise to the field called electromagnetism. The field that we are going to study in this course actually has come out of Faraday's law. It is Faraday's law because of which today the information can be sent or can be broadcasted at very high speed. It is Faraday's law that today we are having communication, satellite navigation. It is Faraday's law because of which today the world as we see is only because of Faraday's law. So actually Faraday's law has revolutionized the way today the world looks. So we can say that electromagnetic field theory is actually an important course because it lies behind any kind of modern communication system, whether it is optical communication system or it is satellite communication system or even it is information communication system. It is the electromagnetic field theory, because we will have to remember that light is an electromagnetic wave. So electromagnetic wave, so we understand electric field, we understand magnetic field, and now in this course we are going to discuss electricity and magnetism together. So first, to understand what is field. What is field? Field is a physical quantity defined in terms of position and time. So let us take an example. There could be scalar fields and vector fields as well. So I have scalar fields and vector fields. So now to understand what are these fields, let us take first the example of scalar field. Let us take temperature. We all would agree that otherwise we consider temperature as scalar quantity. So now I say temperature is a scalar field. Temperature is a scalar field. So I can say that temperature is now defined as x, y, z and t, where t is the time parameter and x, y, z are position coordinates in Cartesian system. So I say this is temperature. So now you can say temperature is position dependent. At every point, and for different x, y, z, the value of temperature is different. Okay? So can we say that now temperature suddenly starts to behave like a vector quantity? Well, not really. So let us assume that I have this room, and in the center of this room we have say blower. So I have a big room, you can consider your classroom, and at the center we have a heat convector. Okay. So now as we move away from this heat convector, you will see when you are very near to this heat convector, you will feel very warm. Okay. And as you move away from the heat convector, you will feel less and less warm. So it means as I move away, the temperature is different. Temperature is different at different positions. Now we switch this heat convector off, we switch it off, okay. Then you would see with time. Now here when it was on, at different position the temperature was different, okay. Now you will see at the same position at different time temperature is different, temperature will start to fall gradually. So these type of scalar quantities which in a given space have different values at different positions are called scalar fields. So here we should not get confused. It is definitely not a vector quantity. Okay, it is position dependent. But to define a temperature, we do not require direction. Okay. So this was about scalar field. Then we have vector fields. So generally in electromagnetic field theory, whenever we consider a vector field, we are generally dealing with flux. Flux is velocity per unit area. So if I have a pipe, then the flow of water coming out of this pipe is basically flux of water. So this is the velocity of water per unit area, and direction is normal to this surface area. The direction of water flow is perpendicular or normal to this cross sectional area of the pipe. So in electromagnetism we have two types of flux, one is electric flux and another one is magnetic flux. So these electric and magnetic flux, because apart from having direction, apart from being position dependent, they also require direction to completely define it. Okay. So these are vector fields. Now question is, I said that a moving charge generates electromagnetic fields. A moving charge would generate electromagnetic field. So what is the defining equation? How would we characterize or define this equation? I know that force on a moving charge is generally given by QE plus V cross B, and this can be written as M into V, I would say M d1 minus v square by c square 1 by 2 d by dt. We can even have this m out inside. So I have this defining equation. So this we call Lorentz force. This is the electrical component, this is the velocity of the charge, and this is the magnetic field. Okay. Now I have this universe and there are large number, infinitely large number of charges. So how would I and all these charges might be moving. So how will I calculate that what is the total electromagnetic field generated due to all these infinitely large number of charges? Answer is, the situation is not very complex. If I have infinite number of charge distributed in a space and I am interested in some charge q1, okay, then this force is only defined by the velocity of this particular charge at this position, electric field experienced by this charge at this position, and magnetic field experienced by this moving charge at this position. So at a time it is only an individual charge that matters, but not the whole charges. Okay. So now another thing is, I have group of charge here, and if say the total electric field generated by them is E1, and I have another group of charge somewhere else and electric field generated by them is E2. Okay. This is in a separate space, this is a separate space, and this is a separate space. Now I bring both these groups together in the same space. I bring these two groups of charges in the same space, and I will see that the total charge, total electric field is equal to E1 plus E2. And this is called principle of superposition of fields. This is called principle of superposition of fields. So now to move little further, we will discuss about certain quantities, certain mathematical parameters which are important to understand this course of electromagnetic field theory. The whole electromagnetic field theory is based on just 4 equations, and the famous equations, they are called Maxwell's equations. So we will do these Maxwell's equations in detail, but we all know that in Maxwell's equation there are only 2 operators which are important. Del dot E is equal to rho upon epsilon naught. Rho is charge density and del dot B is 0. Okay. And I can say that del cross E is equal to minus del B by del T. Okay. And there is another is mu naught J. Okay. So these are the 4 equations. So now these equations are not important at the moment. So these are, so if we look at the left hand side, so there are only 2 sets of differential operators. So this we call divergence, and this we call curl. And this operator is the differential operator del, and this is vector in nature and defined as I del by del x, j del by del y, and k del by del z. This we all know. So this is vector in nature, and this when it operates on electric field, it gives certain information. When this del operator is operated through a dot product, then it gives me that how much is the charge content in a closed volume. So this is basically Gauss law, and here I have curl, whether a given electric field is rotational or not. So if you remember from your electrostatic that I have electric field E. If I have electric field E, then I can define my potential as integral E dot dl. I can define my potential V as E dot dl, and then I can say that E is equal to negative gradient of V. I can say that E is equal to negative gradient of V. So now the question is, V, I know this is a scalar potential, field, and the moment I operate this del on this V, I get E, electric field. So can we say that this del operator contains all the information about the position of electric field? It looks like, because the moment this, as far as electrostatic is concerned, the moment I apply del operator on the potential field, on the scalar potential, I get electric field. And from here, this is for the case of electrostatic potentials. Okay, from here, if I take del cross E, then this is minus del cross into gradient of V, and that is equal to 0. So in electrostatics, electric fields are irrotational in nature because their curl is 0. As far as electrostatics is concerned, their curl is 0. So in electrostatic, electric fields are irrotational, but that's not the case here. Here this electric field, in electrodynamics, this del cross E, curl of E is negative rate of change of magnetic field. That is, the magnetic field is induced, or the induced magnetic field will try to oppose the cause due to which it was generated. Okay. So del cross E is equal to minus del B by del T in the case of electrodynamics. So there is a very significant difference, although this difference is subtle, but this difference is significant. In electrostatics, electric field is irrotational. The curl of electric field in electrostatic is 0, whereas in electrodynamics, curl of electric field is not 0. That is, del cross E is not equal to 0. Okay. This is an important difference between electrostatics and electrodynamics. Now we have these two operators, divergence and curl. So it is very important to understand the physical significance of these operators. Let us take divergence. I have a positive charge and I have a negative charge. Okay. The field from the positive charge field always comes out of the positive charge. So I have something like this. And electric fields always terminate at the negative charge. So things, when they are closely spaced, then these field lines go like this. It will originate at a positive charge and it will terminate at negative charge. This is the field pattern. Okay. Now what I do, I draw a small, I take a small volume somewhere here. I take a small volume here. Okay. So here is my charge. So let me I take a volume which encloses this charge, which encloses this charge. Okay, this is the small volume. So we can draw it like this. Here I have the small volume. Okay. So this encloses this small charge. Now fields are going in. Okay, fields are going in. Okay. Now if I look at the fields that are going in and the fields that are coming out, at this point I will see that more field lines, more electric flux is entering this volume, but less is coming out. But less is coming out or nothing is coming out. You can see here a lot of fields are going in, lot of fields are entering into this volume, but nothing is coming out of this volume. So it means here I have a point, like you can consider a case of a pipe, water pipe. Water is going in, but output is 0. There is nothing coming out, nothing coming out. So what does that mean? It means there is a sink inside, somewhere water is going, there is a sink point where all the water is getting accumulated. Similarly, here also input is maximum but output is 0. And such case is called a case of negative divergence. This is called the case of negative divergence. Right? On the other hand, I consider a volume here. I consider a small volume here. Now if you see, I am not considering what is, so you can see nothing is, these arrows are going like this. Okay, here arrows are coming like this. Okay, so if you take this point, you will see that nothing is going in, but lot of field is coming out. Input is 0. That is, here now the case is reversed. Here nothing is going in, but water is continuously coming out. So it means there should be a source somewhere inside the pipe. You are not giving anything from this end, from the open end, but lot of water is continuously flowing out. So it means there is a source inside the water pipe. So here we can call this point as source of electric field. This point is the source of electric field, and such cases are called cases of positive divergence. Okay, this is the sink point. This is the sink point, right? So these cases, so what I want to emphasize here is positive charge, the electric fields from a positive charge will always have positive divergence. So let me write it down, that electric field from a positive charge has positive divergence. Okay, so it is also called a source point, and electric field similarly from a negative charge, will have negative divergence. Okay. Now, the question is, we have sort of understood what divergence is. We will deal this divergence in greater detail in our forthcoming lectures. But now we have another important quantity which sits there in the Maxwell's equation, and it is curl. So we all know curl is the measure of rotation. Curl is measure of rotation. So now question is, what do we mean by rotation? So if I take the same case, okay, and if suppose I have a charged rod. I place it here. I have a charged rod which I place here. Okay. So you can consider, say this is positively charged. So you can consider that we have a distribution of positive charge which is sitting in this electric field, right? Now question is that these charges are static. Now because this is positively charged, so this will try to attract, whereas this will try to repel. But now you can see that the strength of electric field here, and strength of electric field here is constant, because these charges are there, and at a given plane, this is a plane, at a given plane the strength of electric field is constant. So it means now the force experienced here by here and here is same. So what would happen? This charged rod will slowly move in this direction. Okay, this will slowly move in this direction. On the other hand, let us consider a different situation. I have electric fields, and suppose I draw electric field like this. The length of the arrow shows me the strength of electric field. Okay, so here you can see the strength increases, and here it is more, and then it decreases again, and it decreases further. Okay, so length of this arrow shows me electric field is in this direction. Now what I do, I put a charge sheet in this electric field. Now you would see here the electric field is more, here it is even greater, and here it decreases. So this charge rod will be slightly rotated by some angle theta along the direction of electric field, and if I move little further, it will again be rotated. Okay, so it means this changing electric field have the capability or capacity to rotate a charged rod or rotate the charge distribution. Okay, you don't consider it a rod, you consider a linear charge distribution. So it means changing electric field can actually rotate a charge distribution. So such changing electric fields are called rotational fields, whereas static electric fields are irrotational in nature, because they cannot rotate a charge, but definitely they can accelerate. They can definitely accelerate a charge, but they cannot rotate. So it means this electric field has got curl is not equal to 0. So here I have electric field, and this is a charge. This is a linear charge distribution. And here in this case curl is 0. In this case curl is 0, because the charge distribution is just accelerated, but it is not rotated. So we will have to remember that constant electric fields are irrotational in nature, as we had seen, that because it is irrotational in nature, and this was just now shown through the gradient relationship also. And changing electric fields, if the magnitude of electric field is not constant, definitely that electric field will have a non-zero curl. Okay, so this is the basis. These things we should understand very clearly, before starting this course. And as I told you that Maxwell's equation, in the whole course we will be only dealing with Maxwell's equations under different cases. So it is very important to understand Maxwell's equations and understand these divergence and curl operators. Now, till now we have been dealing in Cartesian system, but generally, because charges are spherical in nature, so fields radiated by them, the fields that are originated from a point charge, is generally spherical in nature. So it is also very important to understand or to know how curl, divergence and gradient will look in cylindrical and spherical systems. So now in our next lecture, we will try to derive these mathematical operators, mathematical functions in 3 Cartesian systems, that is Cartesian, spherical and cylindrical. And then we will move on to our course on the physics of this course. So first we will develop some mathematical concepts which are necessary for this course, and then we will move on to the physics, and then probably you will find this course more interesting. Thank you very much for today.